Alright, welcome to our last video on rotation, where we have to talk about angular momentum. And this is a pretty straightforward application of extension, I should say, of linear momentum to systems that are rotating. It can get messy once we start to get into the weeds with algebra, but the concepts are very similar. Okay, there's not a whole lot new conceptually. One or two things that are a little tricky, but angular momentum really isn't that big of a deal. So, what's the definition of angular momentum? You see I have I wumbo here. We'll talk about what that means. So think back to linear momentum. Why do we talk about linear momentum? Well, it turned out that calculating an object's momentum, or more specifically a system's momentum, was useful in certain interactions, such as collisions or explosions, because under certain circumstances, the momentum of that system was conserved. It didn't change from before the collision to after. So just like linear momentum, angular momentum, and by the way, the symbol for angular momentum is capital L. Sorry about that. Capital L is useful in situations such as collisions or explosions, two objects that are together then exploding apart from each other, cause objects or systems to rotate. Okay, angular momentum is calculated because it is useful. That's it. It's calculated because it's useful and because we can use it in situations to determine the result of a collision or an explosion. The equation, and this is, I believe, on your reference tables for angular momentum, is the following. L, angular momentum, equals I times omega. Now, I want you to think about that. Think about the linear momentum equation. P equals mv. This is just the same equation, but with the angular variables. Instead of P, which is linear momentum, we have L, angular momentum. Instead of mass, M, we have moment of inertia, I, which is based on mass, but is kind of the angular counterpart to that. And instead of V, we have omega, or as I like to call it, wumbo. There is one other thing that you do need to know, however. For a point object, remember, a point object is just a small, compact mass, doesn't have any real shape or volume to it, rotating, point object of mass m, I should say, rotating a distance r from an axis. Let's recall that the moment of inertia for that particle would be mr squared. Any other moment of inertia has a coefficient in here, which a positive coefficient in there that changes the moment of inertia. Recall that the moment of inertia for this is I equals mr squared, and I also want you to recall that V equals R times omega. Why those? Because we want to specifically discuss the angular momentum of a point object. The general formula for angular momentum is I omega. I for a point object is going to be mr squared. And if V equals R times omega, then that means that omega must be equal to V over R. What that's going to do is cancel out one set of R's, and we are left with this. The momentum, angular momentum, for a point object is equal to the mass multiplied by the distance r from the axis of rotation, times the velocity, the linear velocity of that object. Okay? And this will come in useful, comes in handy in our gravitation unit. Okay, so Just like linear momentum, if you had multiple objects in a system that were moving, you simply added up those objects' momenta, and that was the total momentum of the system. Angular momentum is the same way. You just have to be careful whether the which way the objects are rotating or moving. So, if more than one object is rotating, then what we can do is we can simply add the angular momenta together, or if the objects are moving in a different direction, rotating in a different direction, subtract if different direction. And I just want to make a note before we get to our example. It's a lot like torque. Angular momentum has to be defined with respect to something. L must be defined with respect to some axis of rotation. Even if the object is not technically rotating about that axis, it still has to be defined. You still have to pick what's called an axis of rotation and define the angular momentum relative to that. All right, let's get to our example. This one's going to get a little involved here, and we got a decent amount of writing to do first. So let me draw the picture, or actually, I'll write the situation first. We have a mass m moving at a velocity of v, hits an object of mass big M at one end. A distance L over 2 from its center of mass. Here's the picture. We have a point object of mass m. It's moving with a speed of v. And it hits and sticks. We haven't gotten to that part yet, my apologies. So hold on, let me write that part. We are going to assume a perfectly inelastic collision. We are also going to assume that little m is much smaller than big M. So there's what happens. We have little m moving at speed v. It hits this big kind of rod of mass m and length L down here, so at L over 2 from the center of mass. And we're going to assume that the rotation is about the center of mass. In other words, it's going to be rotating about this point. There's our axis of rotation. So, we have a couple of things to talk about here. What's going to be conserved? There's a collision. Usually in collisions, we know that linear momentum is conserved if the net force on the system is 0. I don't see anything that would say that there's a net force on this system, so I'm going to go ahead and assume that the net force is indeed 0 and linear momentum is conserved. Now, is angular momentum conserved? This is kind of similar. Instead of looking for a net force, though, to see if the net force is 0, we're instead going to be looking for a net torque. Is the net torque 0? And what that question boils down to is there anything preventing this system from rotating? And there's not. So what we're going to say is that if big M is completely free to move, then both P and L, linear momentum and angular momentum, are conserved. In other words, if it is free to translate, to move from place to place, and it is free to rotate, to spin. If both of those are true, then P and L are conserved. Now, once this hits and sticks, obviously this is going to be a pretty complex motion. It's going to be spinning around and moving to the side. Different parts of this system are going to be moving at different speeds at different points in time. Different parts of that system will have different linear speeds at different times. So when we go to use the conservation of linear momentum, and we try and find the speed at the end after the collision of the system, we will be finding the speed of the center of mass. So therefore, V in the conservation of momentum equation is V of the center of mass. So, let's start there. I start with conservation of linear momentum. P naught equals P. There's one object moving in the beginning. It would be, oh, I'm going to call this V naught, excuse me, my bad. So it has a momentum of m times V naught. Once it sticks, the momentum is m plus big M times V. Very simply, the linear momentum of the system, or the linear velocity of the system after the collision, is going to be equal to little m V naught over little m plus big M. And that's the velocity of the center of mass. So I'm going to put VCOM. Okay? Linear momentum, pretty straightforward. The ideas for angular momentum are also pretty straightforward, but the algebra can get a little messy. One of the questions you might have, because we said that L is conserved, is wait a second, if this object wasn't spinning to begin with, but now it is spinning, how is that conservation of angular momentum? In other words, how does this mass here, if angular momentum is conserved, and this is going to have angular momentum afterwards, how does this object have angular momentum right now? How does the mass have L initially? Well, the answer is that objects don't actually need to be rotating to have angular momentum. Doesn't make a lot of sense, okay? We'll just go with us on this one, okay? Because this can cause angular momentum, we can say that this must have some angular momentum to begin with, even though it's not rotating, okay? The reason it has angular momentum is because it's about to hit this object a distance r from its center of from its axis of rotation. So what we're going to do here is we're going to use that the angular momentum for this object at the beginning is mvr, with r being the distance from what we call the line of action. No, that's just a fancy name for the path of the mass. Oops. To the axis of rotation. We saw a similar thing in our torque unit. So, we're going to have, all right, I'm going to move this up, so we're going to start to need some more room here. we're going to, since this object is free to rotate, or the system is free to rotate, we're going to have L naught equals L. Momentum is, angular momentum is conserved. Initially, the angular momentum is given by mvr. At the end, it's given by our actual angular momentum equation. I shouldn't say actual, they're both actual angular momentum equations. I omega. Now, m is the little mass, v naught is the speed that it comes in at, and r is how far away it acts from the axis of rotation, or how far away it is, or how far away the path is. That path, if you look, the dotted line is like this. That's the path of the mass. If we were to just continue, at its closest, it comes within L over 2 away from the axis of rotation. So r is L over 2. So I'm going to apply that to the entire fraction here. Now, what's I? Remember that the moment of inertia for a mass, a point mass, is mr squared. And I'm going to give you the moment of inertia for a rod. That's 1/12 ml squared. And one of the things we learned when we talked about moments of inertia is if you have a complex system with multiple parts, you simply add the moments of inertia together. By the way, I should define that this is the moment of inertia about its center, since it's rotating about its center. If it was rotating about an end, then it would have a different moment of inertia. But we don't need to get into that. The moment of inertia of the system is simply the sum of the moment of inertia of its parts. So the moment of inertia for the mass and the moment of inertia for the rod. For the mass, we have m and then r squared. R is the distance from the axis of rotation. That's L over 2 again. But this time it's got to be squared. So we're going to take care of that in a little bit. Plus 1/12 capital M L squared times omega. And by the way, if I didn't say what we were doing, I think I didn't and I totally forgot. What we're trying to do is we're analyzing these systems. Our goal is to find the velocity of the center of mass and omega in terms of what we already know. This I can just tell right now, it's going to be a nightmare to do algebraically, but we're going to try anyways. To start simplifying, I'm going to pull this up here. mv naught L over 2 equals ml squared over 4 plus 1/12 capital M L squared times omega. I'm going to choose to pull an L over 12 out of this. Okay, now that's going to sound a little weird. L over 12, I'm pulling an L over 12 out. Okay. Actually, I'm going to pull L squared over 12 out. So on this side, I'm still going to have mv naught L over 2. And on this side, I'm going to have L squared over 12. Now, what's left in here? M, and then what would it have to be in order to get multiplied by this and go back to m times L squared over 4? It would actually have to be 3m, with 3 up top. Because if I multiply this by L squared over 12, I have 3ml squared over 12. 3 and the 12 will cancel out, so there's a 4 on the bottom, and I have ml squared on top. Plus, what's going to be left here is just capital M times omega. You'll notice that I have an L on this side and an L on this side, so one set of these L's will cancel, that L will cancel, and this squared will cancel. I have a 2 and a 12. The 2 will cancel. This becomes 6. And ultimately, what I'm trying to do is I'm trying to get omega by itself. So I'm going to multiply both sides by 6. I'm going to divide both sides by, let's see, 3m plus capital M times L. Rearranging algebraically, I get omega equals 6m v naught over 3 little m plus big M times L. Very messy algebraically, but not that hard to get to if you follow the rules for algebra. So we've seen that we can use conservation of linear momentum to find a linear speed. We can also use conservation of angular momentum to find an angular speed. Only a couple more topics to talk about. We kind of already touched on this, but it's good to go over again. When can we say that the angular momentum is conserved? When do we say linear momentum is conserved? So, these are the questions you ask yourself. If you're wondering if linear momentum is conserved, you ask yourself, are the objects that are in the system, are they free to move without restriction? In other words, there's no friction acting on them, there's no hands touching them, there's no strings or springs or anything like that from outside the system. If yes, the answer to that question is yes, then P is conserved. As far as angular momentum goes, you ask yourself, are the objects not free to move linearly, but free to rotate? If yes, then L is conserved. Those are the questions you need to ask yourself, okay? This isn't just a guessing game as to whether one is conserved or not. You literally ask yourself those questions. Is this object free to move? Is it free to rotate? That will guide you to see what conservation laws you can apply. You can apply both of them. You might have to apply neither of them, okay? If an object is not able to rotate freely without some other outside force acting on it, and it's not able to move, then neither of these things are conserved. So let's, real quick, what's an example of momentum not being conserved? Because we've done lots of examples where linear momentum is conserved. We've done lots of examples where angular momentum isn't conserved. Let's do an example where P isn't conserved, but L is. Consider this. What if an object hits a bar that is pinned down at one end? In this case, it can spin about that one end. Angular momentum is conserved, but the pin exerts an outside force on the bar and keeps it from translating, from moving linearly. But it's free to rotate. That would be an example where L is conserved, but not P. And then finally, just one real quick thing about linear momentum and the center of mass. If, and we've said this before, but it goes, we might as well say it again. If linear momentum is conserved, then the center of mass of the system doesn't accelerate. Okay, that's it on angular momentum, excuse me. You can see that there are, it's mostly extensions of linear momentum. There's not a whole lot new going on here, but that's pretty much it. That's, I mean, really what we got to be aware of is when angular momentum is conserved, knowing the equations for it, which are right on the reference tables, understanding what I is, understanding, probably the biggest jump is understanding that object can have angular momentum even if they are not rotating about something else. That's it. Our last topic is, or our last unit is gravitation, and those videos you will be seeing shortly. So long.